Okay, so this is the latest update on ShrinkWrapper. First of all, the licenses are free. All you need to do is click on the link, which will open up your default mail client, and it'll send a request to us for a license, and we'll give you a free license at no cost. So in this example, I'm going to be opening up a pretty complex model. It's a model of a bridge that was originally developed in Revit, and we exported that to STL, and that's what it looks like. If we head over to Revit, this is the Revit model. So I've removed a bunch of stuff that is unnecessary just to speed up the processing time, but still we're left with rather complex geometry, which will result in lots of triangles and nodes and vertices. So, we try and strip out the elements in Revit in the view by hiding stuff that we don't need to see. But in terms of creating a wrapped geometry, a solid volume of the exterior of this model, you can imagine if we had to manually do that, we'd have to create a profile around each of those deck segments and then extrude them across. So by exporting this to STL using ASCII format and setting the resolution to coarse, we can speed up this process using ShrinkWrapper. So this is what it looks like when we import it. We'll use the triangulation method here. There's two methodologies. One is triangulation, one is point cloud method. I'm setting the relative alpha and the relative offset values there, and I'm also setting the decimation value, because once it's finished doing all of this, it's going to actually reduce those triangles for us. And it's going to just present better. So it's busy running. It'll take quite a bit of time, a couple of minutes, maybe 5 to 10 minutes on this one. And, I just paused the video there to speed it up a bit, but this is what it looks like when it's finished. So it's taken 362 seconds, and it's generated that wrapped mesh for us. And you can barely see it here, but when I convert it to solid, so we've got a mesh in the model, but we're converting it to a watertight solid, and there you can actually see the results. And if we switch off the original model, here we are left with the wraparound of the entire geometry as a singular solid B-rep watertight model. We can export this to various formats, so DWG being one of them. You can also export to STL and OBJ files. So we'll just export this and see what it looks like in AutoCAD, just kind of test it out. And while that's happening, it's actually already finished. I'll just fire up the AutoCAD and then open up this model, and we can see what that looks like. Now, while we're waiting for that to happen, you can see that it's actually decimated the mesh there. So we had a count of 11,000 nodes and 22,000 triangles, and it's reduced that to 1,817 vertices and 10,900 and something triangles. So it's cleaned it up quite a bit. You can, of course, switch off the decimation if you don't want to reduce the triangle size and keep it more uniform. But I'll just head over to where I've exported this model to, and we'll open that up and have a quick look at what that looks like. And you can see the file size is quite small. It's only 1.3 megabytes for this huge model. To give you an idea, the original Revit model was 1.6 gigabytes. Once I've stripped out all the stuff we didn't need, it was down to about 250 megabytes. The STL file itself was 180 something megabytes, and now we're down to 1.3 megabytes. And as you can see there, we're selecting it as a 3D solid in AutoCAD, so it's perfect. It's watertight, and of course, the resolution is fairly reasonable on this model, considering the scale. But we can further reduce that by playing around with the relative alpha and the relative offset values. If we increase those values, then we'll get an even finer resolution. Obviously, that'll take a bit longer to process. So, but still, it's going to save you a lot of time. And when you use CFD applications or math, game rendering applications, then this is a good way to go. There's another methodology, which is the point cloud methodology. So for this one, I'm going to load a familiar Revit model. This is one of the Revit architecture sample models from the previous versions of Revit. And in here, in this methodology, we set up a point cloud. So we create the sphere, and wherever the horizontal and vertical lines on the sphere intersect, it's going to create a camera or a node point. And then we create this grid by specifying X, Y, Z spacings. And you'll see those red dots. Now imagine you draw a line from each of the intersections in the sphere through those points in the bounding box, those red points, and we try and identify where we hit a target on the surface. That is where it's going to create a point, and that's going to result in a point cloud like what you see on the screen now. Now, this is not the most densest point cloud. It's got about 100,000 points in it. I guess if you get to 1 million, then it would be a lot more accurate and detailed. So, the results are not going to be that great on this one. Again, we set the relative alpha and the relative offset and grid snapping and the decimation values. And we're going to run the wrap points command on this one. And when it's finished, it's going to create that mesh again. And once we've done that, we can investigate it a little bit. Of course, the resolution on this one is not super high, like I mentioned before. We can set it much finer. It will take longer. This one took about, I guess, 5 minutes to run. If we want a high resolution and get a real accurate output, we would decrease the grid spacing and increase that relative alpha and relative offset. But yeah, perfect.